Hello everyone, today we will be going over the concept of trees, and without any further hesitation, let's get started. And now going over the data structure for trees. So trees are an extension of what we already covered for linked lists as well, where they are comprised of nodes, and these nodes are stored together in a hierarchical structure, where we have one node that is considered the head, which would be called the root in this case, and then that node is also connected to other nodes as well on the left and right called children. And these are nodes that are connected to the root based on left and right, and can also have various subtrees as well. And in general, trees can have as many nodes as possible. This is a crucial fact to keep in mind as we move forward between graphs and binary search trees. For this is what general trees have a key distinction on. It's really encompassing the amount of nodes that they can carry as well. And for the sake of this lecture series, we will be focusing on balanced versus unbalanced trees, where balanced trees are considered a type of tree that can have as many nodes as possible. So say for instance we have one node right here, it can have 1, 2, and 3, and then 3 as well. And well, this node right here can also have 1, 2, and 3, but this balanced tree have all the respective nodes, hence the name balance as well. And this provides efficient complexities or tasks to be taken in place, such as insertion, deletion, and also efficient lookup times for time complexity O log of n. Well, meanwhile, an unbalanced tree, as the name suggests, has a significant disproportion of nodes, really, for instance, in one area versus another area, hence the name unbalanced as well. And they technically have a time complexity of O of n, which is considered not so efficient for various tasks, but relatively efficient. And for us to be able to actually go through in trees as well, we have 3 different processes that we go through in order to actually go through and scan throughout a tree. We have pre-order traversal, where pre-order traversal is where we visit the root node first, and then move over to the left subtree recursively, and then to the right, and we print out everything that we have in place. So we go to the root, then we go to the left, as far left as possible, and then finally to the right, where we would go to the most bottom that we have and go all the way up for pre-order. And technically we would have one, then we go for the bottommost on the left, and then after we have covered the bottommost on the left, then we go to the rightmost bottom and move up accordingly. So, and then in order, as the name suggests, we recursively visit the left subtree first. Hence, we would have 2, and then 1, and then 3. In that case, hence going in order, where we store everything from left to right. And then post-order traversal is that we recursively visit the left subtree first, then the right, and finally the root node, instead of having the root visited first for pre-order in that case. So we would have left, right, and then up right here. Left, right, up. So it would be 2, 3, 1. Instead of, for our pre-order, we would have 1, 2, 3. And in order would be 2, 1, 3. And then post-order would be 2, 3, 1. So that would be that case. And there are also 2 different search methods as well that are widely used in terms of trees, and also widely used for graphs and binary search trees. But for the sake of trees, going over depth first search, DFS, and breadth first search, BFS, where depth first search is a traversing algorithm that explores as far down a given branch as possible before backtracking, which means that this can be implemented in the following traversal methods, where we can apply for pre, in order, and post-order traversals as well. And these algorithms can be used to be able to help us determine how we want to be able to scan. So as the name suggests, depth first search focuses on the depth of a given tree, where we are going to be going to the leftmost, for instance, and then the rightmost, where unlike breadth first search focuses on the level. So say for instance we are starting directly from the left at 2, breadth first search will actually go from 2 to 3 all the way up to the root that we would have. And the differences between depth first search and breadth first search is that depth first search uses a stack to be able to store everything that we have already visited while breadth first search focuses on a queue where we are storing everything that we have also visited, where breadth first search goes based on level, and depth first search goes on the depth of a given tree. So it goes left, then it goes right, and then we move accordingly to be able to actually store the rest of our values, so that way we can see exactly what we have already stated. And going over the example we have, so in the following snippet, we have a class definition of our node that we have already set in place. We have an integer of data, which indicates the type of data we're storing for our nodes. We have the node left, node right, node int value over here, and the following data. And we initialize our left node, and our right node is indicated over here. Then we're performing in order traversal, whereas what we do is that we, for in order, after we first visit the left, and then we're going to get the data of the left, and then we finally get the rightmost after we have visited the root as well, so that way we can see exactly what we have stated. Now, we have our root node that we first declare over here, and then we have our left, and then we have our right as well. Because in order traversal allows us to be able to go from left to right, and then we perform the following function that we have, and we have the following output in respect. So now that we have already covered the basics behind this overview of trees, let's head over to our practice problems. So we are given the task to implement both a balanced and unbalanced tree and perform the following operations. First, we need to insert a node into the tree. Second, we need to remove a node from the tree. Third, we need to perform an in-order traversal. The next, perform a pre-order traversal. Finally, perform a post-order traversal, and perform breadth first search, then depth first search accordingly. So what we will be doing is that we will be focusing on the balanced tree first to do the following tasks. Then we will move over to an unbalanced tree and eventually compare both of them together for us to be able to fully understand exactly the differences between both trees and their respective operations as well, to understand the behaviors in full. And now let's go over our first problem for a balanced tree. Now, prior to, I'm actually going to be creating a type of file for you folks, so that way we can actually see the nature of the tree that we have. And this was going to be a header file that we will use throughout the rest of the trees lecture series. And to do so, I'm just going to go do the following. We're going to have our header file. I'm going to call this TreePrinter. And we are creating this so that way we can use all the functions all throughout the rest of the problem for when we are calling in main versus just having the class directly inside of the main file accordingly. It makes everything cleaner. So we are going to be writing this all together, but you can also feel free to skip this chapter at the same time. But I am going to have this here so that way, one, not only to get fully accustomed with the C++ syntax, but to actually fully understand how and why we are be able to print the following trees that we will have accordingly. So feel free to code along, type along, but in the meantime, let's just get things started right here. So first thing I'm going to do is that I'm going to include the library. So I have a stream. I'm going to have include o manip, and then we're going to have include dq, include cmath, include string, and then we're using namespace std. We're going to have a class called TreePrinter, and then a public instance that we will have, and we are going to have 5 of these. Type name node 1, 2, 3, 4, 5. This will be for the height, printing the branches, printing the nodes, printing the leaves, and then printing the whole tree together. So the first part that we're going to be doing will be for the height. So we will do int height of node for a given root, and then if the root is equal to the null pointer. We're going to return 0, and then we will return 1 plus the max of the height with regard to the root at the left and the height of the root on the right. There we go. Now the next part, we're going to be printing the branches. We're going to be doing so by creating this function void print branches for int branch length, int node space length, int start length, int nodes in this level, constant dq node, and nodes q. We'll have a type name. In fact, I'm just going to expand this fully so we can see. So we'll have type name, dq node, constant iterator called iter, and I'm going to set that equal nodes q. Yeah, there we go. At the very start. And then we're going to have this for loop for int I is equal to 0, I is less than nodes in this level. Yep, calling upon this part. We're going to divide by 2, and we're going to increment I, and we're going to output the following. I is equal to 0, or set with for the start at the beginning of the length, minus 1, just to initialize, set with for the node space length, minus 2. Iter star iter, this will start, or slash indicating for the branches, or space because we're going through each row accordingly. Let me just make sure if we have the following. Iter set with There we go. We're supposed to set it right there. That's what we're trying to do. Make sure your parentheses are already set up in place. And then we're going to have count set with 2 times the branch length. It's indicated right here. Plus 2. Iter or more branches as well. And then count endl. Next part, we're going to be focusing on the nodes, leaves. We're doing void print nodes. Int branch length, int node space length, int start length, int nodes in this level, constant dq node star, and nodes q. And we'll have a type name dq for node star is indicated above, kind of like what we did already. So we'll just put that right there. Then we'll have a for loop for int I is equal to 0. I is less than the nodes in this level, but we're not divided by 2. And we're going to increment I since we're printing the nodes and the iterator. And we will output count I is equal to 0, or set with start lin, and then set with nodes space lin. I'll put this. Alright, start iter, and iter to the left, or set fill, and set fill, for following space. There we go. Then we're gonna have another cow and another cow. Set width for branch length +2, or iter, or to string, iter with the following key, then the following space as well. For the final one, iter, and iter right, or set fill, or set fill right here for following space. I'll put set width for the branch length. And then set fill there. So we determined the differences between the nodes and the spaces as well, if need be. Now we're going to be focusing on printing the leaves, and we're going to be doing so by void print leaves, int indent space, int level, int nodes in this level, constant dq, node, and nodes q. Make sure that we're also checking throughout each part. Make sure everything is clean. So we have type name, dq, node, star, for constant iterator, iter equal nodes q begin. Then we'll have for loop for int I is equal to 0, I is less than nodes in this level. We'll have I iterate up, and iter as well for the count. I is equal to 0, or set width, indent space +2, set width 2 times level +2. Then we have star iter, or to string star iter with respect to our key here. There we go. Then we will count and L. Then finally, we are going to put this whole thing together, and we are going to be doing so by the following: void print pretty for node, root int level, and then int indent space, and int h equals height for our root, int nodes in this level will equal 1, int branch length equals 2 times int for power of a double of 2, respect to the height, minus 1, minus 3, minus level, times int power for a double respected height, minus 1, int nodes space length space length, yep. 2 plus the level plus 1 times int power 2.0 with respect to the height, int start length equal branch length plus 3 minus level plus indent space dq with respect to the node, nodes q push back within our root, and for int r equals 1, r is less than height, and we are going to be incrementing r. Which will be indicated for our given root that we will be going through to be able to print out. Semicolon here, and then we will do print branches, branch length, node space length, start length, nodes in this level, nodes q, branch length equals branch length divided by 2 minus 1, node space length equal node space length divided by 2 plus 1, and then start length equal branch length plus 3 minus level plus indent space, and then print nodes branch length, node space length, start length, nodes in this level, nodes q. Right, and then we're gonna have this for loop for int I equal 0. I is less than nodes in this level, I plus plus node for the current node equal nodes q front, nodes q pop front. If the current node, what we'll be doing is I will have our q being implemented for putting all the nodes on the left hand side. Excuse me, current node to the left, and then we'll also do that for the right. And else nodes q will initialize this to be the null pointer. For both the left and the right, and then we will have nodes in this level multiplied by the product of 2, since we are focusing on both the left and the right side, and we are going to be printing the branches for the branch length, node space length, start length, nodes in this level, nodes q. Then we're going to print the leaves indent space level nodes in this level, and then nodes queue. And should be good. Let's just build this to be sure that this is all fine. Build succeeded. And then this is our tree printer that we will be using throughout the rest of our series for trees. I'm also going to put this in the comment section for reference and all. And now let's head over to inserting a node. Now focusing on inserting a node into a balanced tree. So overall, first thing that we're going to do, as usual, is that we are going to include a library. So we're going to include iOS Stream, or depending on whatever IDE you use. We're also going to include algorithm. Then we're also going to include our header file that we made, TreePrinter.h, and then using namespace std. And so we'll have class. We're going to use this type of balanced tree called AVL tree. And then we're going to have a public instance right here. We're going to construct our node, where we will have a data point called key, and we're going to initialize the node on the left and the node on the respective right. And then we'll have int height, and then initializing the nodes as well with respect to the data point, key of k, to left null pointer, and then the right null pointer. Height already initialized as 1. Just gonna move this out. There we go. So putting that there. Now we're gonna initialize our root, node root, AVL, and our class instance tree, starting with the root, and then null pointer. This is how we initialize first. And what we will do is that we'll have our height. Get a balance, check the right side for insertion, and then check the left side for insertion. And then we will insert the node. So first thing we'll do is that we need to check the height. We do so by having a integer function height, int height, node, with return node, or node at a respective height. There we go. And then we'll get the balance, int get balance of the following node with respect to the node, and then we will return a node or the following height of the node on the left, and minus the height to get to where we are inserting it. Right. Here we go. And then we're going to check the right side for insertion. We do this by a rotation in this case, and I'm also going to put this right here just to, have it be quiet. So node right rotate for node of y. It's going to be node at x equals y at the left, and then node of t2 is going to be x at the right. X right is going to equal y once we are rotating on y left, will be equal to t2, and then we are going to get the height of our following max height. Left. Plus 1. X. Respect to the height. Equal max height. X to the left. Then height. X to the right. Plus 1, and then we are going to return x. Yep, looks good. Now we're going to check for the left side for insertion. We're going to do this by left rotate. So node left rotate with with respect to node of x. In that case, we're going node y is equal to x right, node t2 is equal to y left, y left is equal to x right is going to be t2, x to the height is going to equal max of the following height with x left, and then height of x right plus 1. Make sure parentheses are reset in place, and then we're going to have y's height equal max height with y left, and a height of y right plus 1. And then we're going to return y. Now, next part, we will insert the node. We can do this by the following node function that we have. Node insert for node int key as the following parameters that we have. If there is no node, we're going to return a new node with a data point indicating that edge case, and then if the key is less than a node for the at the key for our insertion, we're going to insert at the left. Node left equals insert with node left key, and then else if the key is greater than the node key, that means we will go to the right and then insert the node at the right with the respective key as well. And otherwise, in our base case, we will return node and check the height. Right, and then get the balance as well, and check the balance of the tree. So check the height with the following node height to see if there's any adjustment, equal 1 plus max of the height with node at the left, height node on the right. Get the balance by doing the following: int balance equals the function we made for get balance of the following node. And now we're going to put in the Boolean conditions to check the balance of the following tree. If the balance is greater than 1 and the key is less than the node at the left with the respective data point of the key, then we're going to return right rotate of the following node. Then if the balance is less than -1 and the data that we have is greater than the node at the right data point, we need to return left rotate for the following node. And then in this case, for the next condition, if the balance is greater than 1 and the key is greater than the node at the left data point with respect to the key, we're gonna have nodes, the left node rotate with node left, and then return right rotate for the following node. And if the balance is less than, final Boolean condition, if the balance is less than -1 and the key is less than node to the right and the respective data point of the key, then we'll have node right equal right rotate with the right node. And we will return the left rotate for the following node as well. Finally return the node. In that case, now we will have our main function as well, after we made our AVL class. So the main function, the way it's going to be built out, is that we will have AVL tree, we'll call this AVL, and then we're going to call upon our TreePrinter and call this printer as a following from our header file as well. Then we're going to have the AVL root. I have 3 instances of inserting AVL.insert, AVL.root with 10, and we're going to have other ones as well. 30. And then we're going to output nodes inserted into AVL tree and L and printer dot print pretty. Yep, we got that. We have AVL dot root. The initialize that and then space 0, and we're going to return 0. There we go. And I also have the corrected TreePrinter as well in the following solution at the same time. So in that case, we would do that. But yes, this is inserting a node into a balanced tree. And now let's go over and try to figure out how do we remove a node from a given tree. Now, when we are removing a node from a balanced tree, we need to do the following. So we're going to keep everything that we did beforehand when it comes to inserting a node specifically in a balanced tree. The big key difference is, because we always need to check the balance consistently throughout the rest of the tree, is to do the following. So after we have done so, we need to create a min value holder to check the current node. And then we actually delete the node. So the way I'm going to go about this is have the node function, node min value, node with node in the parameter, and then node with the current node here. And while we are checking on the left hand side for the current node that we're looking for, and setting a pointer, we're just checking our placeholder right now. And then return. Cool. Wait, okay. There we go. Set in place, and now we delete the node. And we do so by the following. Node, delete node with the node at the root with respect to the key, and then if it's not the root, then we return the root as an edge case, and if the key is less than the root's data, which is root key, we'll go to the left and delete the node specifically on the root left side, it's data, and then else if the key is greater than the root key, we will go to the right side and delete the node on the respective right side key. And otherwise, what we will do is that if the root on the left is nothing right here, or the root the right also has nothing. We're going to go down our following tree by having a temporary node, and then we're going to swap. So node temp equals root to the left, or root to the left with respect to the right. And if it's not the temp, what we will be doing is that we'll have the temporary be equal to the root, and then we'll have the root be initialized as a null pointer. Otherwise, we'll have a temporary root right here and set the following values accordingly. Finally, delete the temp, and else, in this case, we'll have a node temp equal the min value node from what we're getting on the right hand side, and then we will check for the key, the data really, and we'll also check over here on the right hand side, because we're looking on the left and then the right, delete node with root right and temporary key as well. And we're not done yet, so we also need another case where if none of the following root, we're going to return the root, and then we'll check the balance. Height, check the balance as well, and we'll do so by the following. Root height equals 1 plus the max of the height with respect to the root left, and then height with respect to the root on the right. We get the balance. Since we're dealing with the balance tree, and we can actually just take from what we have done already beforehand, except we're going to not just return a node, but a root. So in this case, since we're putting in root, we'll do root to the left, replace the node with root, 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 and return root. There we go. Root, root. Alright, so we don't have any errors there, and so what we're going to be doing is that we will now delete we will have avl root equal avl.delete node with avl root at a specific point, so we'll have 20. That means node has been removed from the tree. And then we're going to print out our updated tree as well. just checking. And let's run this. There we go. Yes, that's what it does. It takes 20 from what we already did at the root, and it's going to place 30 at the following top at the same time. And so yes, this is how we delete a root specifically. Because we notice in particular that once we delete 20, we have 30 at the top, and typically the left-hand side contains key values that are going to be less, while the right side is going to be more typically, and so hence when we delete 20, 30 is replaced as a root, and we have done so accordingly. And so yes, this is how we remove and delete a following node as well. I will have these, so right over here, going through, we keep all the stuff that we did before, except for the differences is that we will have our we're focusing on the root to know exactly what to replace and what to actually set up and specifically delete at the same time. So yes, this was removing a node from the tree. Now we will move over to performing an in-order traversal. And now going over in-order traversal, the way we will be conducting such, it's actually really easy to be able to go over and know exactly what to put. Alright, so for in-order traversal, what I'm going to be doing, this is going to be the easiest function that we have, and we can also apply this for other ones as well. So all I'm going to do is void in order with node with root, and if the root is going to be in order, we check the left side. So we're implementing components of recursion as well. Root of key, we get that data point and we start outputting it right here. And then in order for the root on the right. And I'm just going to fix that. There we go. There we go. And now, what we will be doing is this. I'm going to, alright, just double checking in this. So, I'm just going to be doing avl.inOrder root over here, avl.root. In fact, I'm just gonna say in order traversal. Let's run this thing. Build successful. Yep, that is correct. That is correct over what it does. We have the in order traversal already stated. In fact, I'm just gonna put this right here. There we go. In order traversal is 10, 20, and 30. Which is correct. It starts from the left, the root, and then 30 as well. So we already see 10, 20, 30 nodes. Oh, okay, never mind. This. I should probably just like move this right over here. There we go. Okay, so we have in order traversal of 10, 20, and 30. Already stated before. And we also have selected node that has been removed, so that's just coming from over there. But really, yeah, this showcases in order traversal. And now let's head over to pre-order traversal. And now for pre-order traversal. Now pre-order traversal, we're just going to do the exact same thing that we did before for in order, except for the differences is just the ordering of the specific way we're outputting the nodes. Now, since we are treating each of the nodes with respect to the root And just using principles of recursion, we can just print out the root. So we would go void pre-order a node at the specific root, and if the root right here, we would go through the root key, and we will output the following over here, and we would use pre-order root at the given left, and then pre-order for the root at the given right. Just going up, checking to see everything. Yep, and so we check the current node in particular that we have over here. This is when after we have inserted the following, and then we're checking the left and the right. Heights as well. Yep, within our class. So pre-order is using the root to be able to actually check each node accordingly by setting the node as a root, and we're going through each order. It looks like we go through the root and the left and the right. So now for us to go through this pre-order traversal, what we gotta do is avn.pre-order. Yep, looks good over here. Let's run this bad boy. Yep, that is correct. Pre-order traversal. Hang on, let me just there we go, that's better. Yep, that's correct. Notice how we go from the root already, then the left, then the right. That is how we do pre-order. And now let's do post-order. And now we are going over post-order. So post-order traversal, again, we're going to apply the same principle that we did before. So we'll just have the void post-order node for the root. And then if we're at the root, post-order root at the left, post-order at the right, and count root key right here. There we go. And now we're going to do the exact same thing we did before. Make sure you spell everything correctly. Post order, AVL post order. There we go. Make sure it's all corrected right here. Sorry, post order right here, post order down here. Yep, that is correct. That is correct. So we have post order already set. So we have pre-order. Post order function is already set up in place. We see 10, 30, and 20. That is good. 10, 30, and 20. That is the nature of the post order. It goes directly based on the levels, really. Left, right, and then to the root. Works its way up. Pre-order focuses on the root, leftmost, rightmost, and in order it goes from left, root, all the way up to the root, and then to the far right. And so yeah, that was post order. Now let's head over to breadth first search. Right here. And now focusing on breadth first search. So breadth first search overall is a type of search technique where we are actually searching throughout the entire tree, but we are focusing on the levels per se, starting from the top down. So say for instance we have our following tree that we have with 20 as the root, and we have 10 and 30 accordingly as its children. Now for breadth first search, it will scan through the rest of the tree, but really it's going through each level. So it starts from 20, goes from the leftmost node to the rightmost node, and it goes based on levels. So imagine that there are circles really circling from the top all the way down from the left to the right that are being drawn in this type of fashion. So that is the best way of describing breadth first search. Goes down by level. And so we will be able to replicate this by doing the following. So let's do our function BFS right here for including the node and its root. And mind you, there's a key difference that makes breadth first search is that breadth first search uses a queue, which means we will go back up to what we've already done for this balance tree, and we're going to include a queue for the STL library. And we'll be doing the following. So we'll be checking in particular and searching throughout our root. We will return and initialize our queue using a node. And we will push all the instances whenever we are visiting each node and putting it inside of our queue by using the push function, also known as the in queue. And so while the queue is not empty, we will have a node set up to the front because queues go first in, first out, and we'll output the node's data by going node key and putting in spaces accordingly. Then we're going to pop the queue indicating that we've already visited, and if the node to the left is where we're at right now, we're going to push the information of the node that is at the left into our queue. And then we'll do the same thing for the right, check both the right and the left because we're already checking the root, and keep searching throughout the rest of the tree using breadth first search. So I'm going to double check. Looks like it's all good. Now we're going to output our breadth first search function by doing the following. Breadth first search for this, and we would go breadth first search AVL root. Let's build this, make sure it's all good. Alright, let's run this bad boy, and does the same thing. Ready to go right here. Yep, it does it. So we have our tree 20, 10, and 30 as what we've already inserted. And kept everything organized. And then we have breadth first search accordingly. Go from 20, 10, and 30 in that case. Going through each level, having those imaginary circles per se, going from the top all the way down to the bottom, at the leftmost to the rightmost. And so let's move over to depth first search. And now focusing on depth first search. So depth first search, as the name suggests or states, focuses on traversing and searching through a tree within the depth mode. So we're going to start with our root, but then we're actually going to go from leftmost depth all the way back to the rightmost, sort of like a giant circle per se. So depth first search would go to the leftmost and then goes to the right, outputting the following. So I also did a test beforehand just to be able to clarify. So if we have a following tree right here, we have 20, 10, 30. There's like this giant circle that it's already going through from the leftmost. It'll also go to the other subtrees as well, to the right. And depth first search is would be considered in that case. So breadth first search versus depth first search. There are key distinctions between the two. So breadth first search, we can imagine little circles right here going through each level, but depth first search is a giant circle going to the leftmost all the way to the rightmost. And so the way we're actually going to construct depth first search, another key distinction, is that breadth first searches also use queues, but depth first search use a stack to keep track of everything. And as we know before from our previous videos, that stacks are can be considered a stack of plates where it's last in, first out, and that's just a general principle to keep in mind. So the first thing we're going to do, we're going to include the library of stacks. It's called include stack, so we have to call that from the STL library. So we're going to be focusing on depth first search by doing void DFS, and then I'm going to take the root as a parameter, so node root. Then if we're not at the root, we will just return just to initialize, and then we're going to initialize our stack with stack node for S, and then we're going to push our stack with the root count as a parameter, so we go through continuously, and while the stack is not empty, we'll have node equal s.top, indicating that we're going to have the node at its given top, and we're going to output the following data by doing count node key, indicating the actual data of the specific node, and put it in the list accordingly. Then we're going to pop the stack so we can go through each component of data. And then if the node is particularly at the right, we will push the information of the stack on the right hand side, and the order is very critical, so that way we actually can replicate the nature of it. So right here, node left. Beforehand, def for search to start from left, then to the right, where in this case, within our function, we go from we have right and left accordingly, just to push everything already set in place. So I'm going to go down for def for search, similar to ref for search functionality, def for search of the balanced tree, def for search, AVL root. Let's just run this bad boy, see if it goes through. And yes, it does. It does go through. So we have the following tree that we have. Then we have the following outputs, 10, 20, 10, 30. It goes through a big circle, and we have similar outputs because of the size of our tree, namely. So we have 3 points. So just for general context, def for search uses stacks, ref for search uses queues, and def for search can be thought of as like a big circle that starts from the root and goes all the way down and all around. And ref for search can be tiny circles where we start from the root and go from the leftmost to the rightmost. So just a few things to be able to describe and communicate on. Now let's head over to unbalanced trees. And prior to going over our unbalanced tree, let's just go over the full structure of that we have already developed. So we included our TreePrinter header already, and then we have our main class as well, focusing on the balanced tree that we have already made. We focus on the structure of the node, and then we initialize our height, get a balance. We rotate the right and the left to ensure the balance of the following tree. We did insertion, as stated over here. We've also checked the balance as well after we've inserted, and then we also removed a node, and we also deleted a node, and thus checked the balance as well after we deleted a node. Another protocol we need to do. We performed in order, pre-order, and post-order traversal, breadth for search using a queue, and depth for search using a stack, making sure that we are still using the balanced tree, and we have the following outputs as well. So this is just a general overview from what we have already covered for a balanced tree. And now let's focus on inserting a node into an unbalanced tree. So to be able to kick things off, what I'll be doing is that we will be importing our library. So we have include iOS stream. So we'll have queue, stack, and TreePrinter file that we have, and we'll be using namespace std. I have a class called binary tree. In a public instance, we're going to construct our nodes. Int key node to the left, node to the right, and initialize our node int k key k left null pointer, right pointer will be set to null. So we initialize everything. Node root binary tree root null pointer, and node insert node int key, and we will be doing a Boolean condition of if we're not at the node, then we will return a new node with the respective key. And if the key is less than the node specifically at the key, then we will insert at the left, node left equals insert node left key. Otherwise, we will insert right, let's insert node right key, and finally return the node. And now we will import our, make sure that we have our semicolons already set up in place. There we go. Make sure we have everything set up, all cleaned. All right, now we will have our main function, binary tree, bt, TreePrinter, printer, and then we'll have bt root equal bt with the function that we just made, insert, and we'll have the root that we're importing, and then specifically 10, and this time we'll put 5, and count nodes inserted in the unbalanced tree. And L. And then we will do printer print pretty bt root. One, 0. And finally, as our base case, we return 0 in the main function. So, there we go. Make sure it's all good. Alright, let's run this thing. And the nodes are inserted correctly in the unbalanced tree. And now let's head over to remove a node from the unbalanced tree. And now we will be focusing on removing a node. So in order for us to be able to remove a node, what we need to do is that we need to do what we did before, as previously when we were working with the balanced tree. Since we are checking in particular on the following root, what we will be doing is that we will have a check with the current node, and then we will delete a node. So this is how we do. We are going to be doing node, min, value, node, node, node. And while we initialize the current node to be the node we are looking for, we are going to be searching through and looping around current, and current on the left hand side is equal to null pointer, because we're just initializing left, and we'll have current equal current left as well. Finally, we will return the current node we are at, and then we will delete a node, and we're going to be doing so by the following node function: node delete node, node root int key, and if it's not at the root, we return the root. And we'll be doing a series of checks to determine if we're at the following. So also we will return root, there we go. So if the key is less than the root data point at the key that we're looking for, the root on the left hand side we will go for root left key, else if the key is greater than the root key, then that means we go to the right. So root right equals delete node root right key, and then otherwise we will do the following: if the root at the left is equal to the null pointer. We will have a temporary note. Right. And we will delete the following root and return the temp, so that way we know exactly what we are going for. And else if the root on the right is equal to the null pointer, we initialize node temp equals root at the left, and then we will delete the root as a placeholder and then return the temp. And then we will have node temp equal min value node on the right, and root key equal the data point of the temporary node. And then we will go for the right hand side to delete the node root right temp key as those parameters. Return the root, yep, that's what we do. Now we're going to go down and we'll be doing the following function. We will be doing bt root equal bt dot delete node, and I'm going to go with the root that we have, and I'm going to select 20 to delete. Node deleted from the unbalanced tree, and then we're going to print our updated tree that we have. Make sure build everything, and here we go. Yep, and we have done so already. So this was deleting a node from an unbalanced tree by doing the following. We check where we're at, and then we focus on deleting the node by doing a series of checks and balances to determine where the specific node is at, and we deleted the following node accordingly. And now performing in-order traversal for an unbalanced tree. So in order for us to be able to do so, we are going to be creating a void function called in-order, and then have node be the root be inserted as a parameter, and then we're going to have if we're at the root, then we will do the following. We are going to call upon our in-order function to get the root on the left. We're going to output the data root key over here, and in order of the root to the right. And then what we will be doing is that we will be outputting our in order traversal, and we're going to be doing count in order traversal of binary tree, and then bt in order of bt root. That should actually be able to get us already set up. Yep. And in fact, let me just clean this part up. There we go. So yes, so we have in order traversal of the binary tree with 5, 10, and 20. That's what we have done. We go to left, top, and then right. Much like in the case of what we did for the balanced tree, except we're just putting this in the unbalanced tree. And now going over pre-order traversal. So pre-order traversal will be the following, much like what we did in the balanced tree, except for we're putting it inside of our unbalanced tree, but the principle still applies. So we do go void pre-order node at the root, and then we will be checking, much like in the case of what we did before and what we did previously, if the root will output the count root key right there, and then we do pre-order with the root on the left, and then the pre-order with the root on the right, and make sure it's already built. Yes, it is. And now we will do the same thing that we did before. We do in order traversal, and then we're going to do pre-order traversal. Let me just clean this up. Pre-order traversal. pre-order traversal and the following route. Make sure that we have everything already set up in place. And let's run this bad boy. Alright, and I'll just clean this part up. There we go. So yes, it does what is accordingly. So it goes 10, 5, and 20, much like in the case. 10, 5, and 20 in the pre-order fashion. So we already see that is the nature of pre-order. Now let's move over to post-order traversal. And now going over post-order traversal, so what we did, we just left off from our pre-order and we just moved up all the way to our post-order section inside of our class that we have done thus far for an unbalanced tree. And the way we're going to be writing our post-order is going to be the following, much like in the case of what we did before for the balanced tree, but we're just putting it inside of the unbalanced tree. We go void post-order node root. If we're at the root, then we're going to go post-order root at the left, and then we'll go to the right, and finally output data root key over here. That's what we do. And now we have our function right here. Let's output the post order. So we're going to do what we did before. It's post order, and bt dot post order. bt root. Let's just build this, make sure it's all good, and I'm going to say unbalanced. Just for sake of clarification, they're interchangeable for what we have, because we're not dealing with a binary search tree. There we go, for the sake of simplicity. There we go. Yep, it does so accordingly. So we have 5, 20, and 10. We see in our tree 5, 20, and 10, going by each level accordingly. So we see the nature between all three of the different traversals in an unbalanced tree. Now let's head over and do our breadth first search for an unbalanced tree. And now I'm focusing on breadth first search for our unbalanced tree. So the way we're going to go about this, remember, from what we have already done in our balanced tree, breadth first searches differ from depth first search because breadth first searches uses a queue and go based on level. So we need to make sure that we have our necessary libraries. Yes, we do. We have a queue and a stack already set up in place. And there are also tiny circles that go directly, that are being circled from the left-hand side to the right, so that way we see the order of what we're going. So first thing we're going to do, when time this out, it's going to be void breadth first search with node at the root, and then if we're not at the root, we're going to return, and we're going to have our queue, node queue, call this queue dot push with the root, and while the queue is not empty because we put a root in, we're going to do the following: node at the front, because queues go in, first out, count node key, output the data, and then we're going to pop the queue just to indicate all the data that has already been pushed out. Yeah, and then we'll go directly from the left-hand side with if the node is at the left, we're going to go queue.push node left. We'll also do the same thing for the right. There we go. Yes, yes, and yes. That's how we develop our breadth first search over here. And now we will go over our breadth first search. We do so based on the following: count /n, just to make sure it's all spaced out. Breadth first search of unbalanced tree. I'm going to go bt.bfs with bt.root. And then alright, it's built successfully. There we go. Breadth first search of unbalanced tree. That's going to be 10, 5, and 20. Breadth first search, a good way of thinking about it. There are tiny circles that are being that are invisible but are there, that are going to be circling all the way from to the left all the way back to the right, and hence we already have the output of 10, 5, and 20. It's a good exercise to be able to see exactly how the breadth first search is already conducted, because it goes based on level, from the root all the way to the other children as well. And now let's focus on depth first search. And the way we develop depth first search is much like in the case of what we did for the balance tree. And also keeping in mind, for depth first search, we use a stack. And a good way of thinking about depth first search is just thinking of a giant circle in general of the way how depth first search is already going compared to breadth first search. Breadth first search focuses on levels, so breadth first search would technically have tiny little circles going from the root that are being drawn from the left to the right, much like in the case over here. But for breadth first search, they're more so giant circles to keep in mind. So if there was, for instance, more children on the left-hand side, we would see, for instance, more of an encompass on the left-hand side compared with the right, but we're still going in this fashion of one giant circle compared to breadth first search, where will be tiny circles of levels. But anyway, we develop depth first search by doing the following: void depth first search node here root, and then if we're out not at the root, we return. Then we will have stack node here with called S, and I'm going to push the root into the stack so that while the stack is not empty, we will have the following nodes be pushed, or stacks in general, they're like a stack of plates, so technically we would have the stack already situated at the top. So we will have node equal s.top right here, and then we'll output the data, node key, righty, and then s.pop. And then if we are node right, the order is also very different compared to what we have over the left. So we have node at the right, and we are going to go s.push. Yeah, node at the right, and then if the node at the left, we're going to s.push node to the left. There we go. So that's depth first search over here, in contrast with breadth first search. And what we'll be doing, we'll be going down, much like the case of what we did before. So instead of breadth first search, we'll go depth first search. Depth first search of unbalanced tree, and we just got to do this function right here, bt.dfs, bt.root, and we should get the following. Yep, that is correct. 10, 5, and 20, much like in the case of what we have over here, 10, 5, and 20. And yeah, that was depth first search for our unbalanced tree, much like in the case in the fashion of what we did for the balanced tree, except where we put it in unbalanced. An unbalanced tree can be considered a binary tree in this case and in general. So yes, this was depth first search. And now I'm just going to go over what we have already fully accomplished in our unbalanced tree. So we have already included our libraries using namespace std for the sake of convenience. We have a class and a public instance for our nodes. We have our root. We also have initialized our root as well. We did our insert as well. And then we removed a node. We checked where we were for the current node, and then we looked for, in particular, of our node that we are starting particularly from the root and its data point for the key. We are looking in particular through the root. We initialized at the top, and we're going to use that as a starting point to go through the left and the right side when searching throughout the rest of the tree to either insert from what we've already done, and then moving over to delete. We check the right and the left hand side, and then we also check in particular on if the root has already been deleted. Well, technically the node that we are searching for, but we call the root as that starting point that we are searching throughout the rest of the tree. We perform in order traversal, as we have already stated, 5, 10, 20. If we have already set up in place. We've also done pre-order as well, where we focus on the left and the right. Notice in particular pre-order traversal of an unbalanced tree, 10, 5, and 20. Post-order as well, we do the left and the right, hence going 5, 20, and 10. Then we did breadth first search, and we always use a queue for such. We would typically have the same output that we have, but the key differences is the fashion and order of how searches are conducted. So breadth first search goes by level. So for instance, there's a small circle at the top and smaller circles as well being drawn from the left to the right, or to the left all the way back around from the right. And depth first search, on the other hand, uses a stack, and we use the functions for the stack to be able to keep track of everything that we've visited. And depth first search can be thought of as a giant circle that is going around the whole tree, starting from the root to the left, to the right, and back again. And this is critical for other subtrees as well that could be inside of the unbalanced tree. So yes, this was our unbalanced tree. I will put the following code in reference as well, but yes, this is what we have accomplished for the unbalanced tree. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.